So here, let us know when you think we should start. Okay.
I think it's time. Yeah, maybe you can start with your slides.
Okay. 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 Thank you. Here. Welcome everyone to another demo / webinar session organized by the CAD for Assurance initiative. CADforassurance.org, as you probably all know, is an initiative taken by a good number of people from the hardware security community about 10 months ago to be able to bring together open source tools, benchmarks, and metrics for Assure systems and hardware. And that was the initiative taken October 2020 during this pandemic time. And we got huge response who came up, number of people came up to help with this effort. And Dr. Yejin, Dr. Gangku, Dr. Sung Yo, myself, we reached out to many people to create a rather unique portal so that we can have the relevant research tools and benchmarks metrics in one place. And to our pleasant surprise, over these 10 months, we have got large number of visitors, and you can see it from the Google Analytics figure we have given at the bottom of this, bottom left of the slide, that there are a large number of unique users, unique page views and all those things happening regularly. And we're very, very happy to see that this effort is being viewed positively by the community, and I believe it's helping a lot of you. And if you are willing to share your tools, your metrics, your benchmarks, please do reach out to us, or in the website cadforassurance.org. You will see a link called Upload Your Tool, and through that link you will be able to upload either your tool or benchmark or metrics, and we'll be happy to post them in the website. So before I go further, I will have to acknowledge the sponsors for this effort. IEEE CEDA, that's IEEE Council on Electronic Design Automation, came forward to sponsor this event. University of Florida Warren B. Ames Institute for the Connected World is a sponsor for this event. IEEE CEDA HSTTC, that's the Hardware Security and Trust Technical Committee, a newly formed committee under CEDA with Dr. Gangku and Dr. Yejin, both of whom are here today. They are leading their initiative. So that also sponsored this particular initiative. And then there are several companies who came forward and wanted to sponsor this initiative, including Mercury Systems, Huntington Ingalls Industries, and Northrop Grumman. We really appreciate their help. We also appreciate constant help from Amanda Washburn, who is helping us with the logistics of organizing this series of webinars. Through this effort, of course, on one side, we have this cadforassurance.org web portal, which has all these tools and benchmarks and metrics. But on the other hand, through this initiative, we also wanted to create a series of webinars and virtual panels on hardware assurance, and that's going on for last 8 months or so. We have had 10 tool demos so far, and we have had already 2 virtual panels, and all of them have been hugely successful with more than 1,000 attendees. We have one upcoming panel, I'll talk about that, and one more or 2 more tool demos upcoming in this year, and then we'll continue through next year. So if you're interested to see what has been done, and for most of them, we have also the recording available, I'll strongly encourage you to go to the IEEE CEDA website on CAD for Assurance, or you can also get a link for those in the cadforassurance.org website. And we really appreciate all the support we have received from the community who have come forward to share their tools and benchmarks and metrics, as well as to present their tools to the wider audience through this initiative. We are definitely very, very thankful for that help. So with that, I'll talk about the upcoming virtual panel. This is the third in the series of the virtual panels, and these panels have been very well accepted by the community. They touch upon some of the most interesting pressing challenges today the hardware security community is facing. The third one in the series would be held on October 8th. That's our usual time, Friday, 11 a.m. Eastern time starting. And we have really distinguished and prominent set of panelists in this particular webinar, a particular panel. And this is focusing on the security assessment and verification for microelectronics, touching upon the metrics and standards of security verification. So I believe you can significantly benefit from participating in this panel, and I'll strongly encourage to register now if you have not done that to attend this panel. Just to talk a little bit more about the panel, as I mentioned, the topic is security assessment and verification of microelectronics. We'll talk about the current practices, the future, and we have, as I said, really distinguished set of panelists. Dr. Sandeep Dey from UF would be the moderator, Kevin Booth, MIT Lincoln Lab, Robert Jones from Intel, Jamin McHugh from AFRL, Air Force Research Lab, Dayton, Sarad Malik from Princeton University, and Keith Rebello from DARPA would be serving in the panel as panelists. So I do encourage you to consider attending this particular panel. We'll try to record, but as you know, the recording for the panels would require permissions from all the panelists, which we do not know as of now if that will be able to achieve. But of course, feel free to attend it live as at when it will be happening. With that, let's come to today's presentation. Again, thanks for joining. We hope it will be very useful one. This one would focus on hands-on hardware security or hands-on hardware assurance. These will be co-presented by Dr. Reiner Dizon, not doctor yet, but he's a doctoral student. Reiner Dizon and Christopher Vega, both are doctoral students at University of Florida. Both are working on hardware assurance, multiple topics in hardware assurance for quite some time. So they hopefully will be able to do a good job with presenting multiple experiments, hands-on experiments on hardware security, highlighting both the security issues as well as protection mechanisms. Just to let you know that this particular set of experiments which they will be demoing today and talking about would be done on a custom designed hardware kit, which we call HAHA or hardware hacking kit. This kit has been developed through funding from National Science Foundation. We do acknowledge that. And this has been developed for last 5-6 years. This is already being used by multiple universities at this point. But most of the experiments can be done on also other hardware platforms as well as the existing FPGA platforms. Some of them would be also can be done on those. In terms of this particular hub module, the design files are all uploaded into the CAD for Assurance website. There are 16 different experiments and detailed instructions for those are also uploaded in the CAD for Assurance website. So feel free to go to the website and look at those. So with that, I will hand over to Reiner and Christopher to talk about the platform and introduce you to the hands-on experiments. If you have any questions at the end, feel free to ask those questions through the chat facility. Okay, so with that, Reiner and Christopher, over to you.
Thank you, Dr. Bay. I'm going to go ahead and share my screen here. Screen. Okay. Good morning, everyone. So as Dr. Benia mentioned, that Christopher and I will be talking about the hands-on hardware assurance demos of select experiments on what Dr. Benia mentioned is a flexible training platform we call the HAHA board. Let's go to the next slide. Okay. So the outline of this webinar is as follows. So we'll go through, we'll introduce the board and how it became to be. They require tools and software that goes along with this hardware hacking board. And then we'll perform a self-test procedure, and then the demonstration of select experiments. So for this webinar, we'll be going through the hardware Trojan attack, the implementation of physical unclonable functions, mod-chip attack, and then we'll conclude this webinar. So the HAHA board, or the hardware hacking security education platform, as you can see here on the right, is a platform developed by EC researchers, and it's a custom board to encourage learning about ethical hacking of hardware components. And as you can see here, it has it emulates a typical computer system. So we have what you would have in a typical computer system, such as an FPGA or a microcontroller. And there are a lot of test points here. As you can see, a lot of header pins around where you can test for different functionalities or affect different functionalities on the board. And we continually label all these components so that a potential hacker can play around with different parts of the board. As I mentioned, we have a microcontroller, which is an ATmega 16U4 and the Max10 FPGA. And both of these components are connected via JTAG pin right here on the left. So they can be talked to via JTAG, or you can affect their functionality using JTAG. And as Dr. Binia mentioned, that the schematic and the PCB layout are all available online. These full boards are sold via third-party vendors. So yeah, that's all for the introduction of the board. So for the required tools and software, there's we need to use a USB to A to B cable to program the microcontroller and to power the entire board. And then to program the FPGA, we would need an Intel FPGA programming interface, and that for example, I'll be using the Altera USB Blaster. And then to observe the signals on the board, you will need an oscilloscope or an analog discovery board. And then for the software, we would require an Intel Quartus Prime software, and anything above version 15 are good. But for this demonstration, I'll be doing everything in version 18. And then for programming the microcontroller, we'll be using Atmel or Microchip Studio. So as Dr. Binia mentioned, we have 16 experiments uploaded on the CAD version's websites. And I took a screenshot from the website and on the website showing all the experiments. So we have, so the first experiment is the self-test, learning about the HAHA board. And then we have a bunch of attacks and countermeasure experiments. And as I mentioned, we'll be focusing on the hardware Trojan attack, the puff, and the mod-chip. So that would be, if you guys are following along, it would be part of experiment 6, part of experiment 7, and experiment 8. So for the experiment 0 self-test experiment, we also give out the test binaries, and I'll be showing how that would work in the self-test procedure. We also include a frequently asked questions document, because over the years, as this course course on hands-on hardware security has been given for a couple of years, there have been questions about this board. So those questions have been compiled and been answered in this FAQ. And then we also have a guide to install those 2 softwares that I mentioned. And then for the 15 experiments, we've also included all the instructions for those experiments. And then for the ones where there are given codes for those particular experiments, we've also provided those codes and a suggested time of completion, as you can see here on the side. So with that being said, I'm gonna now go through the self-test. Oops. So for the self-test procedure, for everyone following the PDF on the CAD for Assurance website, there are 6 parts of this self-test procedure. I'll only go through parts 2, 3, 4, and 5. So I will not be going through how to test the power supply, and the last one is just more for feedback. So part 2 of this self-test procedure is testing out the FPGA and the peripherals, and then part 3 would be testing the microcontroller and the onboard accelerometer. Part 4 is to test the temperature sensor, the RAM module, and the PLL module. And then finally, I'll be testing the EEPROM connected to the FPGA. So I'm gonna get out of presenter view here, and I'm gonna demonstrate the self-test procedure. So to test the FPGA, I've opened up this Quartus Prime software, and I'm gonna go ahead and program the microcontroller. Oh, before I do that, let me show you what the board looks like with all the connections. Let me put that towards the center of the screen here. So this is what the HaHa board looks like. As I mentioned, we require a USB A to B cable connected here. And then we have a Intel FPGA programming interface, and I'm using a USB blaster. And I've already tested, like, as I mentioned, I'm not going to be going to the power supply testing. I've already tested that before this session, but I've already turned on the board here, so everything's ready to go here on the board's end. I'm gonna go ahead and minimize my camera feed here. All right. So for the programming, the first thing is we load this programmer view, and I'm just going to show that real quick how to do that. Tools, programmer, and then we make sure that the USB blaster here is selected, and then I'm gonna go ahead and do an auto detect. And then we'll press OK here, OK in this portion. So it detected 2 devices here, and as I mentioned in the beginning of this presentation, the FPGA and the microcontroller are connected by a JTAG. So it detected both of those devices. So the first one here, the 10M50SA, is the Maxen FPGA, and then this unknown underscore a bunch of hex digits is the microcontroller. So before we do any programming of any kind, we always do this auto detect. Otherwise, when we load in any program, any bit stream for the FPGA, this will not work. So now that that's loaded, I'm gonna go ahead and load in the test code for the FPGA. So I'm gonna go ahead and click on this, change files. I'm gonna go ahead and grab those binaries. So it's called test.pof. If you're following along with the self-test procedure, we'll go ahead and click open. So with Intel Quartus products, there's 2 types of programming files. There's a POF and an SOF. This POF file will actually write it on a non-volatile memory, so that when the board is off, it will reload that program. So that's what we have here. So it will actually load in this test FPGA binary onto the FPGA. Sorry, I also got the chat here earlier at this instance. But this POF process takes quite a bit of time, since it is writing it on non-volatile memory. But if we use the SOF, it will write it onto volatile memory, and that would be much quicker to program. But for the self-test procedure, we have it as a POF file. So let's just give this a moment here to program. So that's what it will look like when it's programmed. So as you can see here, we have flashing LEDs and the 7-segment display showing digits 0 through F in succession. And if I play around with these switches, so right now they're all in the down position. If I play around with these switches, you see another pattern. So that's it's just going up and down. And then if I keep playing around with it, it will just alternate between those two patterns. And another thing, if we press this key button, it will hold one digit and it'll just be coming up. And when you let go, it will continue the other counter. So that's part 2 of the self-test procedure. So for the next part, we're gonna be testing the microcontroller and the accelerometer. So for programming the microcontroller, we're gonna go to device programming. And before I do that, let me pull up my screen again real quick here. So on this board, there's this switch S15. Let me focus in on that area real quick. So this switch S15 has an app and a task position. So for programming this microcontroller, we need to set this to task mode. So if it was an app, we switch it to task and then we quickly reset the board by toggling this S12. So we always want to keep it in the down position if we want to interact with the microcontroller. But to quickly reset, we just do this. We just toggle S12. So now that that's set up, this device programming, we will set it to @mega DFU, and then the device is, like as I mentioned, is the ATmega 16U4, and then we go ahead and click apply here, and then read the device signature, and then we go on memories, and then now I'll load in the accelerometer code. Okay, so let me pull up my camera feed here again. As you can see, nothing really happened on the board right now, and that's because we have to first set the switches down here to 1001. Again, nothing's happening here right now, and that's because we're still on the test mode. So in order for us to get the program running, we need to switch this from test to app. And even if we set it to app, it's still not going to work because we need to reset the FPGA, so or the microcontroller. So I'm gonna go ahead and reset the microcontroller, and now you see here there's some changes in the LEDs. I'm gonna go ahead and tilt the board. As you can see here, those LEDs are switching values. And the 7-segment display is still doing its own counting. So that's how to test the accelerometer and the microcontroller. So now for next part, we're gonna look at the we're gonna look at the temperature sensor, RAM module, and PLL module. So for that, we're gonna go to core disk, and then we're gonna go to tools, in-system memory content editor. Skip everything here as a moment to load, and then I'm gonna go ahead and click on this USB blaster, and then I'm gonna give it a couple seconds here to load. And now that's ready, I'm gonna go ahead and run this in-system content in-system memory content editor for this RAM module. As you can see here, we have 3 values. So let me pull up my feed again. So as you can see here, we have 3 values. So that first value corresponds to the 7-segment display value. That's just to confirm that the 7-segment display is counting properly. The second value is the value from this LED just in hex. So if I tilt the board, let me zoom out a little bit, you see that that middle value is also changing. And then this last value is to test the temperature sensor. So I'm just gonna put my hand here real quick. My finger here real quick. It's taking a sec here. Actually, I'm gonna use this hair dryer here real quick to warm up the chip. I will mute myself. So as you saw there, the temperature went up. So this value is actually the value in Celsius, in Celsius and in hexadecimal. So I can't quickly compute that in my head, but whatever that is in decimal, that's what the temperature is in Celsius. So now that that's done, I'll go ahead and minimize the screen, and then I'm gonna go ahead and have it stop. I'm gonna go ahead and close this window. So before closing this window, there's a bug with this software where if I close this window now, it will crash the entire program. So in order to prevent that, I'm actually gonna click escape here and then close. So that's how you perform read the contents out of the RAM module. And then finally here, we're gonna test the EEPROM, and it's very, very similar procedure as the accelerometer. I'll go ahead and put this in test mode and then go ahead and reset and have that ready. I'm gonna click apply here, go to memories, browse files, and then I'm gonna select this U_EEPROM, and then I'll go ahead and program. And then now I'm gonna switch S15 back to app, and then go ahead and reset the board. So let me show you what's happening here on the screen, on the camera feed. We have the value read from the EEPROM here. It's hex 29 in hexadecimal, and that's what it's showing here. And as I mentioned, if we don't have that 1001, it'll go back to the way it was. So that's the self-test procedure. All right. With that being said, I'm gonna go ahead and move on to the next portion of the demo of this webinar, and we're gonna give demos for the select experiments. So first up, we have the hardware Trojan attack. So just a quick overview on hardware Trojan attacks. Hardware Trojans are malicious modification of electronic hardware, and this is a taxonomy of hardware Trojan, and they are classified according to their trigger conditions and their payload. And as I showed in the slide, there are 2 experiments for hardware Trojan attacks, experiments 5 and 6. So experiment 5 essentially gives an introduction to this hardware Trojan attack by doing digital Trojan. And then the demo that I'll be showing is experiment 6, and I'll be focusing on a temperature triggered Trojan. And on the self-test, I was talking about, or I was testing the temperature sensor, and that's going to be used for this Trojan experiment. And just a quick overview on how the temperature sensor works. The temperature sensor is connected to the ADC IP block, hard IP block on the FPGA, and then the value of the ADC is being sent into the RAM on the FPGA, or on the FPGA, and then that's what's being read on the in-system content memory editor. So for this experiment 6 of hardware Trojan attack, so there are 3 parts. So the first part is to test this ADC temperature sensor, which we've already done, but I'm gonna do that again. But the difference between what I did for the self-test and for the temperature sensor, students are expected to create code to interface the ADC, the RAM module, and the PLL module. And for interfacing with for grabbing the values from the ADC module, we actually have this table that tells you that what the values are, or what the ADC values are, and what they correspond to in Celsius. And as you can see here, as the value goes down, the temperature goes up. And this column right here, I added this column so because that's what's going to be shown on the in-system content memory editor. But on the data sheet for the ADC, you'll only see this 2 columns, and I only took a snip of 28 to 58 Celsius, because that's the range that we're going to be working on for this demonstration. So that's for the ADC temperature sensor. And then the second part is to design a custom system and a payload circuit for the hardware Trojan. And I'll show you what I designed for the custom system. Is a very simple up-down counter an up counter in the LEDs. And then finally, I'll show how to do a temperature triggered Trojan, and Chris will explain what's happening for when the payload is for the payload. So for this last part, we're actually just going to modify the functionality of this custom circuit, and we're going to insert that payload circuit. And then the trigger is that the temperature reaches about above 40 degrees Celsius, and then the payload will show the first digit of the temperature in the 7-segment display. So Chris will again reiterate that when I do the demo, because I'll be muting myself when I do this. Oh, is there anyone in? Oh, hello. There seems to be a microphone in the. Okay, we're good. All right. I'm gonna go ahead with the live demo here. So I'm gonna get out of presentation mode. So for part 1, I'm gonna go ahead and program part 1. Oh, my apologies here. I'm supposed to change files. Okay. POF. It's part 1. Okay. Go ahead and program that. Give us a moment here. That programs. So now that that's done, nothing is actually happening on the board. I'm just showing that nothing's happening. There's that LED blinking, but that's for the microcontroller. We haven't wiped the microcontroller yet, so I would ignore that for this part of the experiment. So that's what part 1 looks like. And then for the custom circuit, I'm gonna go ahead and program that in. Just to make things go a little quicker, I'm gonna use the SLF version here. And then go ahead and program that. We're going ahead and reset all the switches back to all down. So right now, what is showing on here is just a temperature value. But if I go ahead and reset the switch, and or I start a counter and I reset the counter. If I reset the counter, then it'll go ahead and start counting from 0. So that's what the circuit looks like. So now for part 3 here, we're gonna go ahead and insert the Trojan, and I'm gonna be using a hair dryer to trigger the Trojan. So we'll go ahead and reset the circuit here, and as you can see, it functions as if it's the circuit as shown in part 2. Nothing unusual here, but I'm gonna go ahead. I'm gonna mute myself. I'm gonna be running the hair dryer, and then Chris here will explain what's going on. So Chris, when I start here, go ahead and explain what's going on.
Yeah, of course. Yeah, so as Reiner had explained, that there's this circuit inserts a Trojan onto the circuit that we programmed onto the board. So how the Trojan works is that you have the payload and the trigger. So when the trigger for the Trojan is activated, that's basically what's signaling to the that's basically what activates the Trojan and delivers the payload. So in this case, the trigger would be the temperature of the board rising above a certain point, and the payload is that the first digit of the temperature is displayed on the 7-segment display. So as you can see on the camera, Reiner showing, the 7-segment display is currently displaying a 4, which is the first digit of the temperature of the board is at right now in Celsius. So the trigger would be in this case that when the temperature is above 40 degrees, it starts displaying the first digit of the temperature. So if it keeps applying the heat, it should eventually switch to a 5 and then a 6. We probably shouldn't go higher than that.
Thank you, Chris. So what I was going through there is I was going up in temperature just to show the trigger the Trojan going, and then I actually went ahead and decreased the temperature just to show that the value is going down. So that's what I was doing there. So now I'm gonna go ahead and hand it off to Chris here to talk about the physical and clonable function. Go ahead, Chris.
Yes. Yes. Thank you, Reiner. So yeah. So very quickly, since not everyone may be familiar with what a physically unclonable function is, just give a quick overview. So physically unclonable function, or PUF, is a security primitive that uses the process variations or other sources of entropy from a device to create a signature that's unique to that specific device. So you can use this to act as a fingerprint, or which can be used to identify that device, or you can use it for other things such as like cryptographic keys. Puffs can generally be split into 2 categories, which are weak and strong puffs. The strong puff takes in an input or a challenge, and that challenge will determine what the response of the puff is. So in this case, there's a larger since you have multiple different challenges which can be combined to create different outputs, you have a lot of different responses that can be output, and typically this relationship between the challenges and responses is an exponential relationship. So as the amount of challenges increases, the amount of responses typically increases exponentially. On the other hand, you have weak puffs, which are typically just have a single response that is output from the puff. So the relationship between the challenge and responses is linear, and sometimes there's not even an input that you can put into these puffs. It's just on and off. When you turn it on, it'll just give you the single response. And we'll be demoing an example of both of these types of puffs in the live experiments. And then if you go to the next slide. Here we have the 2 types of puffs that we're showing are the SRAM puff and RO puff. So while I'm explaining this, let me just start uploading the program to the board. So first we're going to do the SRAM puff. So this is an example of a weak puff. And what we're doing here is we're using the random startup states of the SRAM cells as a source of entropy to create a unique identifier for that board. So in this case, so in this case, the FPGA doesn't actually have any SRAM, but the microcontroller does. So what we're doing is we're gathering the initial startup states from the SRAM cells on the microcontroller and sending them over to the FPGA through the interconnects. Let me see if I can share my screen really quick. Yes. So here I've already uploaded the code for the SRAM puff onto the board. So this is a very quick example. If we perform the scan chain, we have these memories. These 2 are for debugging, but this one shows the values of the SRAM cells that were generated from the microcontroller, and it simply just shows a string of random characters that were collected from gathering the initial startup states of the SRAM cells, and this would be the signature that you would use as a unique puff response. Stop. Sorry, Reiner, if you could share the slides again. So the other example we have is for the RO puff. So while that's uploading, I'll give a quick explanation of that. So how this one works is that you have multiple ring oscillators that are in this case, we're mapping them onto the FPGA, but you have multiple ring oscillators that you are essentially comparing to each other, and these ring oscillators are used to drive a counter. And so for a predetermined amount of time, these ring oscillators are driving this counter, and after that preset amount of time, you stop them and then compare to the two values, and that is what is used to determine the response of the puff. So basically, you're seeing which of the two ROs or ring oscillators is faster than the other, and then you would have, you know, a set amount of these ring oscillators that you can compare to each other, and the challenges are basically controlling which of the two ring oscillators you're using in your comparison. So in this case, on what we did on this board was we programmed 1024 ring oscillators for both halves of the ROs. So the total is 2048, and then the program in this case is we're using it to collect a very large amount of responses. It's 10,000 in this case. So I write the challenges onto the memory on the board, which it then uses to select the ROs, and then displays the output of each comparison into RAM to be read out. So let me share my screen one more time. Sorry. Okay. So again, we have the three RAMs. So two of these are for the challenges, and then one is for the response. So what we do is we have to input the files. So we have to select the memory relationalization file in this case, which just has this set of challenges. So do the first one, and then the second half of the first challenge set, and then write those to the memory on the board, and then we can collect the responses. So there's just a switch on the board which starts collecting the responses. So when I flip that, you'll see the comparisons happening, and these are the results of the comparisons from the ROs. So again, a 1 in this case means that the second RO was faster, and a 0 means that the first RO was faster. And that's the end of the presentations for the puffs. So I'll give it back to Reiner, and he can continue.
Thank you, Chris. So I'm going to go ahead and talk about our last experiment here, and it's the mod chip attack. So just a quick overview of what a mod chip attack is. It's a small electronic device that can be used to alter or disable artificial restrictions. And they have been used for video game consoles, DVD players, and TV cables. They are also used to replace and override the system's hardware and software protection. And they do that by exploiting the existing interfaces on that device, and in an unintended or undocumented manner. And what we're trying to do is actively manipulate the system's internal communication in order to do so. And a really, really good example of this happened years ago with the Xbox 360. So many, not many, some owners that had Xbox 360s installed mod chips onto their consoles in order to disable or bypass, rather I should say, bypass the digital rights management on the Xbox 360 in order to put in pirated games onto their consoles. So that's an example of a mod chip attack on the field. And if you're following along on the CAD for Assurance website, this would be experiment 8. And what we asked for, what we asked in this experiment is we kind of emulate this attack on the microcontroller and the FPGA on the board. without having to actually install a mod chip onto the haha board. So the mod chip experiment is relatively simple. So the first part here is we read a key that's stored on the EEPROM and we send it to the FPGA. And in this case, the correct key is all zeros in hexadecimal. And on the FPGA side, we check the transmitted key that is sent via the chip interconnections. And then we light an LED or perform a correct functionality if the key is correct. So, and then finally, or not finally, after that we load in a value that's different from the correct key, and that shows a limit functionality, or the chip is not working. And in that case, I will load in a key of hex 01. And then I'm going to show how to hack the board in order to unlock full functionality, even though we've given this incorrect or limited key. So I'm going to go ahead and demonstrate the mod chip attack. So let me go ahead and program in show what I'm doing here first so that so to make sure we're programming here, I'm going to set this back to test. Exit the board. That's ready to go. I'm gonna go ahead and apply the changes here on the programmer, read the digital signature, and go ahead. And I'm gonna go into the mod chip attack and program in the correct key. So that's so now the microcontroller is reading is not only setting the EEPROM to the correct key, it's setting that over to the FPGA. So now I'm going to go ahead and set up the FPGA for part 2. I'll go ahead and change the file here. Go up a couple directories, go to the mod chip, and then I'm going to go ahead and program this SOF file here. And then I'm going to show my camera feed as soon as this programs to show what the functionality is. Oh. My apologies here. Oh. Okay. So as you can see here, the correct functionality, quote unquote, is very, very similar to the self-test. It's just this flashing LEDs, the 7-segment display. So that's the correct functionality. So now I'm going to go ahead and program the incorrect key onto the microcontroller. So before I do that, let me show my feed here. Set this back to test. Test at the board. Apply the settings here. Go to memories, and then we're going to go on to part 3 here. We're reloading the limited key. Go ahead and program that. Show my P here to the right. Go ahead and set this to app. My apologies here. Focusing on there. Set it to app, reset the board. As you can see here, the board is, there's no functionality onto the board. So I'm going to pull up my slides here real quick. So the key is, the correct key is all zeros. And the limited key that I loaded in is the value 1 in hexadecimal. So one way for me to hack this board in order to get the correct functionality is this region right here is the chip interconnection between the microcontroller, and the FPGA. So there's a set of pins here that corresponds to this chip interconnect that also corresponds to pins here in the FPGA, and that's being used to transport the key to the FPGA. So this is right now hex value 1 in binary. So knowing that the correct key is all zeros, what I will do here is take PD0 right here, the lowest, the least significant bit. I'm going to take that, and then I'm going to go ahead. I'm going to refocus here and ground it. And when I did that, as you can see here, I've restored the full functionality of the board. Just to show it again, I'm gonna unplug this pin. It's back to its limited functionality, and plug it back in, full functionality. So that's the mod chip attack. I'm gonna go ahead and go back to presenter view here. So that concludes the mod chip attack. So in conclusion here, we've done a couple things here in this webinar. We have introduced the HaHa board. We went over the required tools and software. We performed the self-test procedure on the HaHa board, doing parts 2, 3, 4, and 5. And then we've introduced, went over and performed 3 select experiments from the website, and we performed live demos for those. And the 3 experiments that we talked about are the hardware Trojan attack, the physical unclonable functions, and the mod chip attack. So the creation of this HaHa board has led to the publication you've seen here, the hands-on learning of hardware and system security. And this is the authors are members of our lab. And as Dr. Benia mentioned, the creation of this board was supported by the National Science Foundation through 2 of these grants, as you can see here on the screen. And this concludes our presentation. Are there any questions?
Thank you, Reiner. Thank you, Chris. Yeah, we have enough time for question and answers. So please post them into the Q&A section of the Zoom, or I don't know, Amanda, if they can unmute themselves and also speak using their mic.
Yes, they can raise their hands and then I can allow them to speak.
Okay. Yeah, raise your hand if you want to speak.
Okay. Do you hear me?
Yes, yes,
Okay.
Go ahead.
Yeah, no, my question was going to be, at least it seems like at least a lot of these things could be done without too much difficulty on a wide range of FPGA boards. I wonder, are there particular experiments that would be difficult to do on any other board than the one you presented?
Okay, Mark, that's a great question, and I will try to answer that, and Reiner and Chris, feel free to add to it. So yes, out of the 16 experiments, let's forget about the first one, that is introducing the board itself. So out of the 15, let's say, I would say half of them can be easily done on any FPGA board, or a little bit more than half. But some of them cannot be done in existing FPGA development boards, and I can give you examples. For example, the mod chip attack, where we are trying to demonstrate a physical modification in the board, and that cannot be done in existing FPGA boards. The POF experiments which you have seen here allow changing the voltage values. That cannot be done. The side channel experiments and fault injection experiments would require someone to be able to monitor the power values for both the FPGA or the microcontroller. That cannot be done. JTAG attack is very hard to do, and also the Bluetooth attack, which we have described in this one of these 15 experiments, that cannot be done in existing board, FPGA board. So yeah, even though quite a few can be done in existing FPGA development boards, not all. Mark, does it answer your question?
He said okay in the chat.
Okay, thank you, Mark. That's a great question. Any other one?
Looks like there's a question for Chris here on the Q&A. How can you access the Atmega SRAM for SRAM PUF, Chris?
Yes, sorry. So the way that you access the ATmega SRAM is it's fairly simple. It's you basically you have to program the microcontroller, and there's a way to do that where you basically just give it the address for the you have your range of SRAM memory array, and you would give it the address for the segment of the SRAM you want to read, and that would allow you to read the SRAM. So the way you do it specifically for the PUF is you have to first you have to figure out find a region of the SRAM that's not overridden on startup. So you just have to basically collect a wide range of the SRAM values, and then determine which ones are not being overridden on startup. And once you've determined a range of SRAM cells that's not being overridden on startup, you can reset the board and then read those values, read the values from that specific range, and then that would essentially be your SRAM PUF. Those would be the values that you use for your SRAM PUF, and then to send them over to the FPGA, there's a set of interconnects on the board, which allows the microcontroller to talk with the FPGA. So on the FPGA side, you're just reading the values from those pins, and then what we did in our example was we read the values from the pin, and then save it to a segment of the onboard memory, and then after a clock cycle, we increment the next segment of memory and then read the values again. We just keep doing that over and over. So, yeah. I don't know if that answered your question.
Hey, thank you, Chris. There are two other questions, and I would let David Barry to speak. David, can you unmute and ask your question?
Okay, I was just wondering how much knowledge the attacker in these experiments had of the code itself. Is this like a white box type attack, or is this more of like a black box attack for the experiments for the HaHa board?
So it would
go ahead. Yeah.
So yeah, so for certain types of experiments, it would be treated like a black box attack. And the ones that we showed you are what do you call it? Some of these attacks are white box, such as the hardware Trojan and the Manchip. So like the Manchip, for example, we knew what the key was, so we knew what attack we can perform on there. So does that answer your question? And Professor, if you have anything else to add, please go ahead.
Yeah. Basically, you're right. It depends on the specific experiment. So again, we have 15 of them. For many of them, we considered that the user would know some part of the designs. For example, the Trojan attack, they would know the design. Now they are let's think about the foundry, right? So they have access to the design. Now they are trying to insert the Trojan into the design. But for mod chip attack, typically these are sort of black box, because you basically take the PCB, fabricate it from a foundry, and then the attacker can simply they have to definitely find out where to tap in to be able to bypass the DRM protection or any other protection, but it can be mostly considered as black box. So depending on the specific experiment, you can the threat model would change from black box to white box or vice versa. Thank you, David. And there is another question in the chat window. It says, "Can power glitching attacks be done in this?" And that's from Raghul Prakash. And again, thanks for asking this question. It's a very good one. We do have a fault injection attack experiment out of the 15 experiments. So we are trying to cover fault injection there. Power glitching is not directly included in that fault injection attack, but power glitching can be included easily. And the board does, board does support power glitching. There are very clearly defined power ports for both the FPGA and the microcontroller, and one can apply noise in those ports to create power glitching effects. We have not done that yet. One thing I would really encourage everyone to do is that, because it's a open forum, this is done for academic dissemination to the community. Feel free to come up with new experiments, either with existing FPGA development boards or any other board you can get access to, and I'll encourage all of you to share that to the entire community. But we'll also try to include power glitching in our future revision of that experiment. Ragul, just let us know if it answers your question. Okay, thank you. So any other question? Anyone else would like to know more about the experiments or the platform?
Hey, through
Yes.
questions, maybe you can conclude the presentation, and maybe you can reintroduce the panel next month quickly.
Okay, so thank you, Iyer. While I'm sharing my screen, can you say some parting words to the attendees today on behalf of HSTTC and IEEE?
Yes. So I mean, the overall the webinar has been hosted for 10 times. So we see a lot of attendees and we receive a lot of requests. So I think we will continue this webinar and educational sessions and panels in the upcoming year.
Thank you, Iyer. Again, I really appreciate the support from IEEE CEDA. I talked about Amanda. She has been extremely helpful, a really valuable resource for all of us. IEEE HSTTC, as I mentioned, a newly formed technical committee. I'm pretty sure Iyer and gang would be looking for volunteers to help with their activities. So be in touch with them if you like to help. But I'm really pleased to announce this panel one more time. I did talk about it in the beginning, and this is the next event organized by the CAD for Assurance initiative. And there will be one more session in November, which will feature 2 more tools, presentation on 2 more tools. All of these are shared in the cadforassurance.org web portal. So talking about this panel, as I mentioned before, it's touching upon a really crucial topic. I think all of you would somehow be able to relate to this topic. It's on security assessment and verification of for microelectronics. It does talk about, or it does cover the standards and metrics and security evaluation process. But when you say security, we are going to be broader than that. And we'll talk about the intersection of security with trust, and the way the panel is chosen is that some of the panelists would focus on IPs or microchips. Some of them would be focusing on rather system level aspects of microelectronics, like printed circuit boards and then the overall system level hardware. So I myself personally is very excited to see how the panel would go. I have high hope, and I do believe that if you attended, you would be having a great experience. You would learn a lot. You'll hear a lot of interesting perspectives from the leaders in this field, and I will strongly encourage that if you're interested, you register for the panel, virtual panel